Consider the complex exponential sequence with frequency omega naught plus 2 by t, omega naught with a frequency where k is an integer, e power j omega naught plus 2 pi k of n equal to k is an integer. This is the frequency in the complex exponential sequence, that is omega naught plus 2 by k. Here k is an integer, so here e power j plus omega naught this one into e power j 2 pi k n. So we will take this e power j omega naught n only here. This is e power j 2 pi k is equal to 1. Means e power j 2 pi k is equal to 1. From equation 1.56 we see that the complex exponential sequence at frequency omega naught is the same as that of the at frequencies omega naught plus or minus 2 pi, omega naught plus or minus 2 pi, sorry 4 pi. That is from the equation 1.56, from this equation from this 1.56 equation we see that complex exponential sequence at the frequency sigma omega naught is the same as that of the, that is complex exponential sequence at the frequency omega naught is the same as that of the at that frequencies in omega naught in 2 pi and omega naught in 4 pi also, plus or minus both. Omega naught plus or minus 2 pi, omega naught plus or minus 4 pi, and so on. Therefore, in dialing with the discrete time exponentials, we need only consider an interval of length 2 pi. Therefore, in dealing with the discrete time exponentials, we need to only in discrete time exponentials we need only to be considered interval length 2 pi, in which to choose omega naught. Usually we will use interval 0 to 2 pi, that is 0 is less than or equal to omega naught is less than to 2 pi, or the interval minus pi to plus pi, that is omega naught in between minus pi to plus pi, that is minus pi is less than or equal to omega naught is less than 2 pi. That is, here we will consider omega naught same as that this frequency 2 pi 4 pi, for omega naught is same only, not changing. That is, in discrete time exponentials we have to consider the interval length 2 pi only, in which I to choose omega naught. Usually we will use interval 0 to 2 pi or minus pi to plus pi. that is here 0 to 0 is less than or equal to omega naught. Omega naught is less than, here open, here closed interval, here less than 2 by omega naught is the less than 2 by, or the interval minus pi is less than or equal to omega naught. Omega naught is less than 2 pi. Here open integral, here open combination, here closed. Okay, the general complex exponential sequences, general complex exponential sequences, the most general complex exponential sequence is often defined as the most general complex exponential sequence is often defined as x of n equal to c alpha of power n. That is, in these complex exponential sequences, defined x of n equal to c alpha power n. C and alpha in general complex number. C alpha are the general complex numbers. Note that equation 1.52 is the special case of equation 1.57 with c equal to 1, c equal to 1, alpha equal to e power j omega naught, alpha equal to e power j omega naught. That is, here c and alpha are the general complex numbers. The special case, this is the special case, that is c equal to 1, c equal to 1, alpha equal to e power j omega naught. Here sinusoidal sequences of x of n, that is a, x of n equal to cos pi n divided by 6, b, p of x of n equal to cos n by 2. Here in sinusoidal sequence, a equal to xn, x of n cos pi n divided by 6, that is x of n equal to cos pi by 6 n. Here this value in x axis n, here minus 12, minus 9, minus 6, minus 3, 0, 3, 6, 9, 12, and so on. Here cos pi 6 n x of n equal to, here then p, in this p figure sinusoidal sequence says x of n equal to cos n by 2, x of n equal to cos n by 2, that is minus 12, minus 9, minus 6, minus 3, 0, 3, 6, 9, 12, and so on. Here p of x1, p of xn, that is here equal to cos n by 2. Here cos pi n 6, pi n divided by 6, here n by 2. So sinusoidal sequences in this n by 2, here like this. In pi by 6 n like this equation. Like this sinusoidal. Okay. Real exponential sequences. If C and alpha in equation 1.57 x of n equal to C alpha power n. If C and alpha in equation 1.57 are both real, then x of n is a real exponential sequence. That is, C and alpha are both real, then x of n is real exponential sequence. Four distinct cases can be identified. Alpha is greater than 1, 0 is less than alpha, alpha is less than 1. That is, a range is 0 to 1. And another one range is minus 1 to 0. That is, minus 1 is less than alpha, alpha is less than 0. 1, 2, 3, 4. And alpha is less than 2 minus 1. Here, greater than plus 1, here less than minus 1. Four distinct cases can be identified. That is, in this real exponential sequence explanation, if C and alpha in equation 1.57 are both real and then x of n is real exponential sequence. C alpha are both real, then x of n a real exponential. That is, if C and alpha are both real, then totally real exponential sequence. So depends upon C and alpha only. Four distinct cases here we have seen. Alpha is greater than 1, 0 is less than alpha, alpha is less than 1, that is 0 to 1, minus 1 to 0, minus 1 is less than alpha, alpha is less than 0, and alpha is less than to minus 1. These four real exponential sequences are shown in figure 1.12. Note that if alpha is 1, x of n is a constant sequence. If alpha equal to 1, x of n is a constant sequence. Whereas if alpha is minus 1, x of n alternatives in value between plus c and minus c. That is, if alpha equal to 1, x of n constant sequence. If alpha equal to minus 1, x of n alternatives in value between c and c plus c and minus c. Alpha is equal to 1, x of n is constant sequence. When alpha is equal to minus 1, then x of n alternatives in value between c plus c and minus c. Sinusoidal sequence. Sinusoidal sequence can be expressed as x of n equal to a cos omega n plus theta. Sinusoidal sequence can be expressed as sinusoidal sequence. So x of n equal to a cos omega naught n divided by theta, sorry, plus theta. If n is dimensionless, then both sigma naught and theta have units of radians. If n is dimensionless, then both omega naught plus theta have units of radians. Both this is also units of radians. This is also unit of radians only. Two examples of sinusoidal sequences are shown in figure 1.3 as before. Sinusoidal sequence in equation 1.58